Empirical formula. Now that we're able to calculate the percent of a compound by the mass of each element, we can begin to identify unknown substances. First, we need the ratio of the number of moles, and that's why we spent so much time on the number of moles, of each element in the substance. This formula, which is based on a whole number ratio, is called an empirical formula. The empirical formula indicates the molar ratio of elements present in a molecular compound reduced to the least common denominator. Least common denominator. Not sure if that's algebra or what, but we'll be using it here. So for example, if we have benzene, which is C6H6, we divide both 6's by 6 to find the least common denominator here. So we just put CH. We have a flow chart. We start with the mass percentage of elements. We assume a 100 gram sample. We find out how many grams of each element we have. Then we use the molar mass, which we just worked on. That tells us the moles of each element. We calculate the mole ratio, and then we have the empirical formula. There is only one empirical formula for a substance, but two different substances can have the same empirical formula. Mathematically, A implies B, but B does not have to imply A. It could also imply somebody else. Okay? And that's because of this lowest common denominator business. So here's an example. You don't have to worry so much about this. Hydrogen peroxide is H2O2. We divide both of those subscripts by 2, and we come up with an empirical formula of OH. However, hydroxide already is in a lowest common denominator, which is also OH. So that implies that, and this implies this, and there we go. The compound para-aminobenzoic acid, listed as PABA in bottles, much easier to say, and it's in sunscreen, is composed of the following elements by mass. We have carbon, hydrogen, nitrogen, and oxygen. Our task is to find the empirical formula of PABA. Let's start with step 1, a good place to start. We're going to convert the mass percentages of the elements to mole amounts in a hypothetical 100 gram sample. Right, that's this guy right here. We'll assume a 100.00 gram, we'll just add a couple sig figs there, amount of PABA to find the mass of each element. So since carbon was 61.31% mass percentage, well, we multiply that by 100 grams and we come up with 61.31 grams of carbon, and we do the same thing for hydrogen, nitrogen, and oxygen. And with any luck, these should add up to 100. You can check that, but pretty sure it does. Step 2. We know the representative mass. We can use the molar mass of each element to calculate the number of moles we have. So let's look at this table over here. We found this column on the previous slide, so if you'd like to review that, go ahead, and that totals up to the 100 grams of the sample. And then this chart, we take the molar masses, and we get this off the periodic table. So carbon, 12.01 grams, that's 1 mole. Hydrogen, the AMU converts over to grams, that's 1.01 grams. Nitrogen has an atomic weight, 14.01, and oxygen, 16. We do the mass, and what we have now, and we go out an extra sig fig, just we can fix that at the end and go back to what we're allowed, but we have 5.105 moles of carbon, 5.09 moles of hydrogen, and so on. So now we've done this, this, and this. And finally, we're doing the mole ratio. So this we have to be a little bit clever on. We look at our moles over here, and this is from the previous slide. Here's carbon, here's hydrogen, here's nitrogen, and here's oxygen. We take the smallest number of moles, and in that case, that would be nitrogen right here, 0.7288 moles. We put that in the denominator of each ratio in this column. So you can see there, 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 and there. We then take the moles for each one of the elements. So here's carbon, put 5.105 there. Hydrogen goes over there. Nitrogen goes here, so that's easy. That's going to divide out and get 1. And yeah, there we go. And oxygen comes here. You divide out, and notice you do not get an integer. You get pretty close, so we're just going to go ahead and round that up or down depending on which integer it's closest to. And carbon, we come up with 7, hydrogen 7, nitrogen 1 because dividing a number by itself gets 1, and here's oxygen. And then we can write it like this. C7, there's the 7, H7, there's the H, then we have N, just one N, and then we have two O's. So there we go. That's the empirical formula. It took us a few slides to do our first empirical formula, but let's show how you can actually do it on one sheet of paper, which is what we have here. Okay, we still have the same steps we did, we're just leaving out all the detail. So we have 1,6-diaminohexane, which is used in making nylon. Okay, that's interesting, we don't need it for this. Here is the mass percentages, and we want to find out the empirical formula. First thing we do, the mass percentages turn into grams. We are assuming a 100-gram sample. So there's carbon, 62.1, hydrogen, 13.8 grams, and nitrogen, 24.1. Next, we convert it to moles. So on the periodic table, carbon, AMU is 12 AMU. We convert that to 12 grams. Hydrogen has an atomic mass that we convert to 1 gram, and nitrogen is 14.01. So we have mole over gram times gram, and we find out the moles of each one of these guys. Who's the smallest? Is it 5.17, 13.8, or 1.72? It's 1.72. We divide all of the numbers in this column by 1.72, and we get this. The moles cancel, and the ratios we get, carbon is 3.01, approximately 3, hydrogen 7.96, approximately 8, and the nitrogen of course is 1. We're dividing 1.72 by itself, so we have C3, H8, N1, which is this. We don't have to put the 1 with the N, we can just leave it as N. So that's the empirical formula. Special cases. Chemistry, like life, is not always simple. You always have exceptions. So this molar ratio business that we just did works very well for most compounds. But in some cases, the math leaves us without whole numbers. So for example, here we have iron oxide. We're not sure what valence we have on iron. So we're going to use the same process, assume a 100-gram sample, and in this case we're told that iron makes up 69.92% of this compound and oxygen is 30.08. First thing we do is we convert that to moles using the molar mass. We have the 69.92, we say that's 69.92 grams because we have a 100-gram sample. Oxygen, 30.08 grams. We divide each one by its molar mass. Iron, 55.85 grams per mole, right off the periodic table. Oxygen, 16 grams per mole. And we get 1.25 and 1.88. Who's smaller? Well, 1.25, so we divide both of these by 1.25, and you can see how we've even shortened this process from the last example. And we find iron is 1 and oxygen is 1.5. So we write it as iron 1, we leave the 1 out, and oxygen 1.5. Well, that's not very elegant, and that's not fair. We can't have 1.5 atoms of oxygen. Doesn't work. So what are we going to do? Think about it for a second before you go to the next slide. Okay, did you come up with anything? Well, we had 1, right, for the iron, and we had 1.5, and we wanted an integer. Well, you can make 1.5 an integer by multiplying it by 2, but whatever you do to the oxygen to keep the same ratio of iron, have to multiply that by 2 also. So you get Fe2O3. That's the empirical formula. And that is iron, parentheses 3 oxide, which we covered in a few units ago. And the 3 there means we have the iron the iron with a +3 charge.